I'm going to make a series of small videos to indicate how we derive the Richardson's extrapolation method. Now, in order to do so, I'm going to need some problem to apply this method to, so that's going to be the subject of this first relatively short video. In the second semester of calculus, you learn that if f is a continuous function, then the definite integral from a to b of f of x dx exists. You also learn a trick. If f is continuous and you can find an antiderivative for it, you can use what's called the fundamental theorem of calculus in order to easily evaluate such things. As a simple example, you might think of the integral from 1 to 2 of 2x plus 3 dx using the antiderivative trick. An antiderivative of 2x is x squared, and antiderivative for the constant function 3 is 3x. Then I put the limits of integration in and subtract, and find out that this integral is 6. This is the way that we're used to doing things in the first and second semester calculus courses. On the other hand, if I try to look at the integral from 0 to 1 of sine of e to the x with respect to x, I don't know a function whose derivative is sine of e to the x power, so the antiderivative trick is not of any use to me here. On the other hand, e to the x is a differentiable function. Sine is a differentiable function. The thing that we're integrating here is a perfectly nice function. This integral will exist, but I don't know an antiderivative, so I can't calculate the integral in the usual way. An attempt to deal with this situation is to go back and think about the actual definition of that definite integral. I'm going to take the interval from x equal a to x equal b and divide it up into a number of smaller pieces. In smaller pieces, this will be the first piece, the second piece, the third one, and so on. In general, these things don't actually have to be the same width, so I'm going to call the width of one of these subintervals delta x with an index I downstairs indicating which subinterval it is. So, for example, delta x1 is x1 minus x0. Here, delta x2 is x2 minus x1. That's how wide the second subinterval is. Delta x number 3 is x3 minus x2, this distance, and so on. To proceed, within each subinterval, I'm going to select a value of the independent variable, in this case an x value. These c values are simply numbers within a given subinterval. I can pick them down close to one end, down close to the other. I could pick the c's to be near the middle. I have complete freedom as to how I locate these c numbers. There are two thoughts that I want to have. One, if I make the delta x's small enough, then if the function f is continuous, it doesn't have much opportunity to change its value on subinterval number I. And secondly, if the function is positive, which was our original motivation for looking at this in Calc 1, then it is up above the x-axis. In that circumstance, I'll pretend that the vertical extent of this subinterval can be described in a reasonable way by f at ci and that the region can be thought of as roughly a rectangle. It's f of ci in the vertical direction, delta xi in the horizontal direction. If I want to know the area of a rectangle, it's just width times height. So f of ci times delta xi in this situation will approximate the area under the graph that goes with just chunk number I. To get an estimate for the total area, I'll add up the estimates for each of the smaller pieces. This is only an estimate though, but we expect if we make the delta x's smaller, it'll be a better estimate. If we take the limit as all of the delta xi's tend to 0, this should be, when I have a continuous positive function, the area under the graph starting at x equal a and ending at x equal b. If you go back and look in the Calculus 1 book, you'll find out that that limit of the sum is actually the definition for the integral from a to b f of x dx. The antiderivative thing, which came later, was a convenient trick to calculate these sorts of things. I'm looking for a sample problem to do my Richardson's extrapolation method on. I'm going to cook up the simplest possible numerical integration scheme. The width of the entire interval is b minus a. If I divide that up into n equally sized pieces, the width of each piece, which I'll just call delta x, is b minus a over n. A, the left end of the interval, is a plus 0 times delta x. x1, which is delta x more than a, is a plus 1 times delta x. x2 is delta x more than that, so you would have a plus 2 delta x. x3 is a plus 3 delta x, and there's an obvious pattern to this. X number I is a plus I times delta x. You should check that x number n ends up being the number b just as it's supposed to. If I want to write one of these sums, I'm completely free to pick ci to be any x number within its appropriate subinterval. For my example, I'm going to pick ci to be the right end of the subinterval. ci will be xi. If the integral exists, then it must be the limit of the sum of f evaluated at ci times delta xi. Here all of the delta x's are the same. My approximation method is going to be the simplest thing I can think of. Instead of taking the limit as delta x tends to 0, I'll select an n. I'll figure out what the finite delta x is. I'll figure this sum out, but then I don't take the limit. So I'm only going to get an approximation here. So I'm going to approximate the integral that I'm interested in with this finite sum. Delta x is b minus a over n, where n is how many subdivisions I decide. And x number I, having selected the n, and therefore the delta x, is just going to be a plus I times delta x. I want to illustrate what I'm talking about here by approximating the integral from 1 to 2 1 over x dx using this right endpoint rule. Using various values of n, I want to do n equals 1, 2, 4, and 8. I'm going to do some examples in which each example has twice as many subdivisions as the previous one. We always want to start looking at a problem whose answer we actually know, and everyone knows how to do this integral from Calc 1. Using the methods that you learned in the first semester of calculus, this integral is the natural log of 2. Since we're going to be wanting to test our numerical methods, I want that answer in decimal, which I can easily get from my calculator. Thinking of n equal 1, I will have only one subinterval. Delta x is 2 minus 1 divided by the number of subintervals, which is 1. That's correct because the horizontal distance from x equal 2 to x equal 1 is 1 unit. The function value is going to be the function value that goes with the right end. My function is 1 over x, so my function value is going to be 1 over 2. I'll have only a single term for my sum, f of 2 times delta x, which works out to be 0.5. The actual value of the integral is 0.6931, so this is not a very good approximation. We wouldn't expect it to be. We have a rather sizable interval, and I'm pretending that the function value is always the value at the right end. For the n equal 2 case, delta x will be b minus a over n. 2 minus 1 over n is now 2. Delta x will be 1/2. x0 will be 1. x1 will be delta x more than that. 1 plus 1/2, which is 3/2. And x number 2 will be 2. The function that we're trying to integrate is the 1 over function, so f evaluated at 3/2 will be the reciprocal of 3/2, and f evaluated at 2 will be the reciprocal of 2. Doing the arithmetic on my calculator again, the n equals 2 estimate for the integral is 0.58 and then an unending sequence of 3's. For the n equal 4 case, delta x will be 1/4. Because my function is the reciprocal function, it'll be convenient for me to write these things as fractions. So x0, which is 1, is 4 over 4. And each consecutive x number will be 1/4 more than that. So 4 over 4, 5 over 4, 6 over 4, 7 over 4, 8 over 4, which is 2. x0, x1, x2, x3, and x4. I have 1, 2, 3, 4 subintervals, and I'm going to represent the function by the function value at the right end. So I'll calculate f of 5/4 and multiply it by delta x, f of 6/4 times delta x, f of 7/4 times delta x, and f of 8/4 times delta x. This will be my n equal 4 approximation to the integral 1 to 2 1 over x dx. f of 5/4 is 4/5. multiply that by delta x. F of 6/4 is 4/6, multiply that by delta x, and then continue doing this until you've accounted for all 4 of the right endpoints of the 4 subintervals. An observant person will notice that every one of those terms has a factor of delta x in it, a factor of 1/4, so I might as well factor that out. Also, there's a factor of 4 inside the bracket in each term. I can pull that out as well and cancel it with the 1/4. The n equal 4 approximation is 0.6345238095. It's very important that I keep all of those digits, as we'll see later. For the n equal 8 case, we proceed in a similar way. Delta x is now going to be 1/8. Each successive x number will be 1/8 bigger than the previous one. A is 1, which is 8/8, so the rest of the x numbers are 9/8, 10/8, 11/8, and so on, until you get down to 16/8, which is 2, like it's supposed to be. My right-end rule approximation for the integral will be a function value at the right end of an interval multiplied by delta x, and then I add up all such things. Since we're integrating the reciprocal function, it's easy to write the function values down, and as before, for this particular function, I can factor an 8 out of each term inside the bracket and cancel the 1/8 out front. We find out that the n equal 8 approximation is 0.6628718,504. And to summarize, when n is 1, our approximation is 1/2. When n is 2, the approximation is 0.58 and then a string of 3s. When n is 4, the approximation is 0.6345238095. When n is 8, the approximation is 0.6628718504. Comparing these numbers against the actual value, natural logarithm of 2, we see that in the n equal 4 and n equal 8 cases, the 6 is correct. The next digit in the actual answer is 9, and neither one of these things gives me the correct digit. So this isn't a very good approximation to the answer. This is even less so. That's even less so. And that's an awful approximation to natural log of 2. One thought is that I can just keep making the n larger and larger to get more and more accurate answers. In principle, that would work, but in practice, it's got 2 problems associated with it. Firstly, it's going to take a lot of CPU time, but more importantly, rounding errors will begin to creep in after a while, and there's going to be a limitation to how big an n is practical to use in any case. In what's to come, we're going to do something that looks like a magic trick. We're going to take this collection of really not very good approximations to our answer and do some sort of trickery to them and manufacture much better approximations to the answer. In this video, I just wanted to set up my scenario. Coming up next, we'll start thinking about how you would combine some of these things in an effort to get answers that are more accurate than any of them. Until then, I hope you're having a good day, and I'll talk to you again soon.